Okay, come on YouTube. So looking further at the motor brake input, I decided in the previous video to, let's see here, to connect this brake input such that this extra Y input can be used as a brake input as well. So this can pull the brake low, as well as the open drain output of this interrupt, which will be pulled low when if there is any fault here. The only thing that's left here is to figure out a way to kind of see which one it is that's being pulled low. And I think that if we just connect this to or actually no, I'll just skip that, because if there is any fault, then it will be apparent when I read the fault register, and if there is no fault, then that means that probably this one got triggered instead. And I got the other one here. Just move this here instead. Delete these two, and let's see here. So we got motor 2 brake in, and motor 1 brake in. And the internal pull-up resistors of the STM32 are used for pulling this line high. Yeah. And then we have, let's see. And I have two other connections here, which I'm thinking to use as PWM inputs. But I just want to check first. I'm going to check the data sheet for this chip. Let's see, where is it? Could it be this one? Yeah. And I want to see the timing. Output data propagation delay, 32 nanoseconds. which means we can easily use this input as a PWM input. And it will in fact support up to 40 volts, yes, in this case. So if I use ENC SG2 and move the PWM to ENC SG2, so basically I'll just move this one, let's see, both of them actually, to one of these. So, and this means I can remove that chip for now. And free up a little bit of the PCB space. Alright, so as far as the outside of the board is concerned, this looks exactly the same, and the only difference is that it now accepts up to 40 volts, and it does not require this chip anymore. Let's do it like this. ENC SG1 and 2 can be removed then. Like that. Let's place test points here for now. Just because I'm not, just so that I don't forget to put something here. But I think I have several signals that may need to be connected directly to the MCU, which are not connected right now based on the list of labels that I've seen so far. So it's quite likely that I'll use those pins up for something else. So SG1 and 2 is all connected. Let's see, so ENC SH1. SH1 and SH2. ENC SH1 should be connected in 2 places. And number 2 should be connected in 2 places as well. Good. So that is fixed as well. And gate 1. Should be connected to the MCU. And gate 2 is connected also to a GPI. Although something I just noticed. So AND gate does need to have a test point attached to it. Let's see. And the same here actually. Okay, and gate 1 and 2 are connected, and moving on to fault 1 and 2. Fault 1 and fault 2. So these ones have pull-up resistors. They don't actually need to have pull-up resistors like that, but I think it was suggested that because the MCU resistors are much higher, it's kind of better to have an external pull-up resistor there. So I'm gonna have external pull-up resistor, but I can see right away here that fault 1 and 2 are not connected. So if there is any fault, there is no way right now to know about that in the MCU. So I'm gonna copy this pin and I'm gonna put it on one of the pins here. We can have fault 1 and we can have fault 2. Connected to these GPIO pins. And actually, I think it's better to, let's see, it's better to move this so that we have A, B, Z. So these two have to be on this connection here. But then we have what we could do actually is do it like this. So let's see. So Z can be connected to any GPIO, and so can both of these pins. So we can do like this actually. And then we have the Z for coder 1 then connected there. And actually it would be a good idea to have encoder signals together. Let's see what we have in encoder 1. NK1. Okay. Yeah, that's a bit random. So I'll place the Z signal here. And then I'll place this one there. Okay, so fault 1 and fault 2 should be now connected, and the fault 2 should be connected as well. Cool. So we can set the fault signals to done. And this is precisely the type of problems that that warrant reviewing every single label one at a time. So gain 1. Gain selects the gain of the current amplifier, so this needs to be connected to a GPIO, which is fine. Gain 2, connected to a GPIO, fine. And the same with over current, but I think I already connected those. I already checked those. Then we have GHA. GHA1. This one needs to be connected to GHA on the chip here. GHA, yes. GHA2 is also connected in 2 places. And GHB1, the second pair of transistors, B1 and B2 should be connected to B2. And C1 is connected to C1, and C2 is connected to C2. And then we have GLA1 is connected to GLA, and GLA2 is connected to GLA2, and GLB1 is connected to GLB, and GLB2 is connected to GLB2, and GLC. 1 is connected to C1, and 2 is connected to C2. Cool. So all of these are green. G and D. Okay, so G and D label is yeah. Okay, so we are starting with the debug connector. Let's go over all of the 62 labels. Bias on the DRV chip connected through a mega ohm resistor to G and D. Let's double check that. I think that was okay. Yeah. Next, GND there. That connects to the GND ref net. DTC and dead time control and PWM mode are both disabled. Or we have the PWM mode is set to 6 channels, so we can see we have pull down resistors there. Pull down resistor, pull down resistor, pull down resistor, pull down resistor. Next one is the ground on the positive line of the current sense amplifier, and the positive 2, ground there, ground there, ground there, ground there, ground there, MPVM mode, bias, ground there, pull down, pull down, pull down, pull down, pull down, and pull down, and the current sense amplifier input ground lines. GND, 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 yeah, GND, 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 and then GND there, GND there, GND there, address 1, GND, address 1, GND, the low side of the resistor, low side, low side, low side, low side, and low side, and another low side. GND on the UX connector, GND there, GND there, yeah, that's it. Alright, so we can say that GND net is supposedly okay. Next, so if there is anything that's not connected to ground, which should be connected to ground, then I probably should have found those faults when I reviewed the components. And since I already reviewed the components, I don't need to check whether some component has to be connected to GND. I'm just checking where the GND net is connected right now. So GPX CS, next one. Let's see. GPX CS connected to that second expander, and here it connects to a GPIO. Let's see. GPX int A. Should be connected to a pin change interrupt, PF9, and a test point. And int B is connected to a GPI pin and a test point. So both of these are okay. And then we have GPX reset, which connects there and to a GPI pin. And then we have GPI CS, So GPX and GPIO, these are two GPIO expanders. Ideally, I should have called them like GPIO1 and GPIO2 or something. But originally, when I put the GPX chip there, it was supposed to be a GPIO expander, but it ended up being the GPIOs that connect to the LCD display. So GPIO CS and GPIO CS there. And the same thing with int A and int B. So it needs to connect there to a test point to the MCU. Yeah, we can take the int B at the same time. There, MCU and test point. So that is done. Now the GPIO MISO and MOSI connects to both GPIO chips. MISO, 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 and MOSI, and MOSI, and MOSI. GPIO reset. Connects to the reset. Great. And the SDK pin is also shared. Connects there, and it connects to the SDK pin there. SPI3 SDK. Good. HAL A1. Connects to the HAL sensor. We lower the voltage from 5 volts to 3.3 volts, and then we clamp this voltage using the diode. And this should connect to TIM3 channel 1 for the first one, and the B should connect to channel 2. So B connects to TIM3 channel 2, and C should connect to TIM3 channel 3, and A2 goes to TIM, let's see, would it be TIM5? I think so. So we have TIM2, TIM3, TIM4 is connected to encoder, and TIM5 is connected to HAL. So TIM5 channel 1 and B2 is TIM5 channel 2, TIM5 channel 3. And we can see that we have the labels here as well. And there's only 2 connections for each label, so I don't need to check the C label. There we go. Alright. In HA, this would be the high side, which will be connected to TIM1. So high side is non-inverted and low side is inverted in my configuration here. So let's see. We have high side HA. Let's go to B in HB and channel 2. Yes, and the C will go to HC and channel 3. And then we have in L A1, which connects to channel 1 inverted. In L B1 connects to channel B, channel 2 inverted. Yes. And C connects to channel 3 inverted. Yes. That's good. So we can let's see. Let's go over the number 2 as well. So we have in H A2 and in HA and in H, and this will be timer 8 channel 1, B, C channel 2, channel 3. We just check here, B connects to B and C connects to C, HC. And then we can go to in LA1, in LA2, and just double check here, LA, LB, LC connects to C, and then we can check here, channel 1 inverted, and B should be channel 2 inverted. Let's see, channel 2 inverted, and C should be channel 3 inverted. Yes. So all of these are green connections between the STM32 and the gate driver, and then we have LCD D0. So we have 0, 1, 2, 3, 4, 5, 6, 7, and it connects to the GPIO expander here somewhere. Let's see. Where is this GPIO expander? There. 0, 1, 2, 3, 4, 5, 6, 7. And all of them have just 2 connections. So I can relight all of them. Now we have the enable, which connects there and there, and LED connects to a resistor, and just drives the LED, the backlight, and let's see, M data, should connect also to the GPIO expander, and read also connects there. All right. An LCD VO is connected. This should be connected to the digital potentiometer. Yeah, connected to wiper there, and to the contrast input on the LCD. Cool. So we have Mach 1, Mach 2. This is GPIOS. Yes, and Mach P reset. So this will be the overcurrent potentiometer. Should connect. Yes, connects to a GPI pin, and Mach P SDA connects to SDA there, and to SDA there, and SCL connects to SCL there, and SCL and SCL there. Good. So reset, SCL, and SDA. Write protect. Next to GPI pin. Motor brake we already handled. Let's see. one per in, connected to a GPIO pin, and here it's driven low. So yeah, so whenever it's driven low, it's going to draw the current from here. So it's going to be the same thing as the open drain output. Okay. And motor 2 connects there. Good. Motor 1 and 2. And reset. This one connects to the debug connector and to a button. That's the two places where this goes. And it has a it has an internal pull-up. So that's why we can just put a capacitor there. So end reset is green. Overcurrent OCV This is the overcurrent mode, which is not connected anywhere. OCV 1 and 1 and 2. So we can connect it to the 3 pins that I have here. Number 2 is connected there. Good. And next is the overcurrent adjustment. Which has a test point and is connected to the potentiometer. And number 2 is connected there. To the bypass, or to the optional static resistor, and to the potentiometer. And potentiometer address 2. What's that? So the MOOCs is not connected. Yeah. That won't work so well. We won't be able to read the potentiometers. Let's make this B. And I need to figure out a way to connect this somewhere here. Let's see. So I do have a few pins here. Yeah, I'm gonna connect it here. I think so. These pins are a little bit special. They cannot drive high loads, so they cannot drive LEDs or things like that. But this is just a selection output, so we can easily just use this as GPIOs and use them to select the potentiometer input. So we have A, B, and C. And also I want to add a few test points here. Let's see. Actually, I'm gonna do like this. Duplicate block. And I'm just gonna move this this reference there. Alright, so we have address lines connected now. Hopefully the fact that I connect them to PC 13, 14 and 15 is not going to matter that much. The only thing I've seen in the data sheet was that these pins are the PC 13, 14, 15, they're low current output pins, but it should work fine for this. So I'm gonna green light all of these, and then we have pot mux. What is that? That's the analog input, so this needs to go to analog input 14. That's good. PWM input. This is connected to timer 10 channel 1 and timer 11 channel 1. PWM 1 and 2. So 1 and we have 2. So that's fine. And then we have SLA 1, which is the midpoint. SLA, SLA. And also it goes to the motor connector. And we have SLB. And the motor connector. And SLC. And the motor connector. Awesome. And all of them are, let's see, yeah, all 6 of them are have 3 connections. So we just need to check that they connect to the right pins. SLA2, yep. SLB2, yep. And SLC2, yep. And then we move on to the current sensing. So A1, which connects to the current sensing output of the prime sense amplifier and then goes to the ADC input. And SOB1 connects there and goes to the ADC input. And B2 connects there and goes to the ADC input. And B1 connects there and goes to the ADC input. Great. Switches. They all connect to a test point and they all connect there. So we have 1, 2, 3, 4, 5, 6, 7, 8 and 1, 2, 3, 4, 5, 6, 7, 8 1, 2, 3, 4, 5, 6, 7, 8. So we can just green light all of them. We also have 3 connections, which looks correct. SW clock. SVD IO. clock and IO. And SWN, what is that? That's the switch enable. So enable pin is not connected anywhere, which means that this wouldn't work. So we have to connect the enable pin somewhere. And I think we can connect it here. Or actually, I'm going to connect it directly. I'm going to connect it directly to the MCU. And I'm just thinking about the use case to power them off. Because maybe we should just tie it to ground. I think that would be a better solution. Then this chip is always outputting the signals here. Yeah, that will reduce the complexity a little bit. Let's see what other pins don't have any connections. This is probably the last one actually. Okay, I'm gonna connect it here. I'm gonna set it there. And if there is anything else that needs a spare connection, then I'll connect it to ground. SWRQ, here's that one. So we have it connected there, and it's connected in there. Okay. Temp mod 1. Connected there, and connected there. And mod 2 is connected to the ADC input and connected there. Yeah, and we have to have it this way because the PWM inputs have to go to TIM 10 channel 1 and TIM 11 channel 1. So temperature is connected, and UART1 debug UART1 TX is connected to TX there and TX here. These two are okay. UXCS there and there. GPI pin, and also this is like a trace pin, which can be let's see, we have the trace clock and we have the CS as a trace D1 trace okay, yeah, just in case we want to use some part of this trace functionality. I haven't actually used the trace functionality. I used the SVO functionality to output because the SVO pin on the STM32 has a FIFO, which means you can write to that FIFO even from interrupts, and you can print out things easily without stopping the microcontroller. So it's like you don't have to wait until the data goes out. You can print out from an interrupt. You can send a notification of an event that happened inside the microcontroller, and it's very, very practical with the fact that it has a FIFO. Let's see here. So I'm not able to click there anymore, apparently, for some reason. So we have the CS pin and UX MISO. Connected there and connected to there. SPI for MISO. UX MOSI is connected there and there. SPI for MOSI. SPI, let's see, UX PWN. Is connected there and to a GPI pin. Good, good. UX RX connected to UART8 RX, and TX is connected to UART8 TX. So we got RX and we got TX. UX SCK. It should be connected to the same SPI for SCK. And SCL is connected there, and IDC2 SCL. And SDA is connected there, and to IDC2 SDA. So that's good. USB 5 volts. That's connected to the USB connector, and then it goes to the 5 volt, just the 5 volt line. USB N. I wonder if I need to let's see. I think actually what I'll do is I wonder if I need to add a diode that leads the current back here, so that the current doesn't flow through the regulator to the input of the regulator. If the main power is turned off and I'm powering over USB. But I think what I do want to add actually is just a 0 ohm resistor that would allow me to remove this connection, so that it will be required to power the board from the main supply in order to connect it over USB. So what I can do here is just place a 0 ohm resistor. I don't want to place any fancy power switching ICs there. It's at least not right now. Not for Rev A. So USB N. Let's see. USB D minus, and it's connected here to USB DM. And P is USB D plus and connected here to USB DP. That's great. VDD 3v3. This line clamped to 3v3, clamped to 3v3, 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 3v3. That clamped as well. That one is clamped to 3v3. That is clamped to 3v3, and everything is to 3v3. Actually, I'm thinking that I should probably just use the same, because on this schematic both 3v3 and 3v3 MCU are connected. So it doesn't really make sense to have two different net names. 3v3, 3v3. Yep. 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 Pull-ups, and they connect there. I can actually just leave it at 3v3 MCU, but at this revision both nets are the same net. And the op-amps connected to 3v3. GPI expanders, LCD. There's going to be a lot of things connected to this single supply. So the question is whether it's whether it can provide enough current for all of these things. Yeah, and this button LED driver. It's quite possible that it may not be able to provide enough current. Yeah. And then we have MCU. Hmm. 500 milliamps. That's way too little for this. Hmm. Let me just fix one problem here. So actually, the way that this should connect is that these labels should go behind the resistor. So I have the current sense resistor here, and these labels have to go behind it, not before it. Because the whole idea here is to sense the current to all of the components that run from 5 volts. And then it also makes sense to add another one here, which senses the voltage. Let's see, actually not even there, but rather after this diode. And this will allow current sensing on the 3v3 line that comes out of here. And then the question is, should we have another regulator? And I feel like we probably should have another regulator here. Let's see, let's move this one. And I think I'm gonna use two smaller LDOs to avoid having one LDO that is rated for higher currents, because it's going to be much larger. So let's see here. This would be the 3v3. See. This will have to go to this connection point. Let's make it clear that the test points are in order to check the voltage on this resistor. And then there will be a way to also connect these two with a 0 ohm resistor, which is going to be unmounted. So this kind of solves both issues. So we have an option to have another regulator here that will provide extra 500 milliamps. And then we separate the power rails between 3v3 and 3v3 MCU. And then we can measure the current that flows to each one of these branches, and see if for Rev B I can use a different regulator and just use one regulator for all of the 3v3 rails. So 3v3 and 3v3 MCU and VDD 5 volt. That goes to the reference, to the Hall sensors, let's see. Should the Hall sensors maybe be powered from the encoder regulator? I think we should use the encoder regulator there. So, because then we have a current limit. Let's see. And is this one? Yes, that's one, and that would be the two. And something that I forgot here as well is the bypass capacitor. All right. Great. So this one is let's see. Let's continue to check the 5 volt rail. So we have to start from the beginning. 5 volts. Yeah. So the main chip is running from 5 volts. That's important in this case. And the input is 5 volts there. 5 volts on the op amps, and the input there is 5 volts. 5 volts on the op amp. 5 volts, 5 volts, 5 volts there, 5 volts for the can. 5 volts for the bypass capacitors there, 5 volts for the can, and 5 volts for the bypass capacitor. Let's see. Right. So we already have one here. So this one actually is. This one is supposed to be that one. I completely missed that one. And do I need to search from the beginning now? Let's see. Yes, apparently I do. 5-volt clamp, 5-volt bypass, 5 volts on the op amps for the outputs, 5 volts there, 5 volts there, 5 volts on the input to the UX, 5 volts to the SPI there. Yeah, alright, so 5 volts is okay. 5-volt debug in. This goes directly to the input here together with the USB. I'm gonna leave it as is. VMOT. We have VMOT connected to the MOSFETs, that's 6. We have VMOT connected to the bypass capacitors and bulk capacitors. VMOT, and the VMOT connected to the input to the voltage sensing. VMOT coming out of the, or connected to the brake resistor circuit. And VMOT is, yeah, that's it. VMOT sense is, on the other hand, just an ADC input. Yeah. And VREF1. These are reference voltages for this, for the current sensing, I think. Let's see. So that has a capacitor, it goes to ref. Then that one is connected to this reference generator. Yeah. VREF1 and VREF2. VSA. So this is connected to the ADC and to the output there. All of them have just 2 connections. Let's say VSA2 is connected there, and VSA2 B1 there, B2 there, and there, C1 there, and C2 there, and there. And all of these are ADC1 and ADC2 inputs. And then we have VSA1 raw. Or VSC row. And VSC2 raw. And VSA1. Yeah. VSA2. VSB1, VSB2. Awesome. So I'm done with the review of all of the labels, and now it's a good time to run the DRC. So I haven't run the DRC on this schematic yet, and now it's a good time to do that. Let me just save all of this to Git. Like that, and let's run the DRC. Let's see if the DRC finds any bugs. Most probably it will find some bugs, but at least it probably will not find the labels that are not connected. Right, we need to annotate the schematic. Annotate schematic. Let's run the DRC. Pin connected to some other pins, but no pin to drive it. Yeah. Let's see what this means. Right. So in our power supplies here, let's see here. Yeah, we need to add the power flag to the to every single rail that is used as a power supply. Power flag. Let's move this one a little bit to the side there. Yeah. So we have two power flags. I think that will fix quite a few problems. Let's see if we need any more power flags. Apparently probably there. Conflict between pins. Right. So U24 and U5. So how do I go to U5? Right, let's see here if so this is a good warning here, because we have connected the slave outputs to the same line, and one way to solve this is to connect resistors between this output and the line itself, just in case two chips drive this line at the same time. We won't get any issues. Let's see. So what is U5? Let's find U5. Can I not find U5 without closing this window? Right. And what we need to do here is double check this, double check both of these chips, and make sure that MISO is an open drain pin. In which case we don't need to have any resistors. But this needs to be checked. Let's see. So I'm gonna go and open up this data sheet. Let's open it up there. So MISO is, let's see, it's called SO in this data sheet. So is this SO pin an open drain pin or a push-pull pin? Oh, there we go. So, SO, serial data out. Let's see if there is an application note about this. So normally this will not be a problem because if the chip is programmed correctly, if the CS line is not pulled low, then all of the meso pins are in high Z. But the situation that I need to take care of is in case there is a programming error. And I need to make sure that I understand what happens then. And that would depend on the type of pins that we have connected together here. Let's see. No, this is not going to provide any good information. I mean, the most obvious way is obviously just connect them together, but what happens if two chips are selected at the same time? Since there is a possibility, I want to make sure that if that happens, nothing bad is going to happen. Let's see. Right. Right, 330 ohms. Sounds good. Let's see what resistors I have. So basically, the way that I would connect them together then, let's see here. Would be through resistors on these lines here. so that any slaves that try to drive the line at the same time shouldn't be able to do that. Or they should be able to do that, but they shouldn't damage each other. So let's see here. If I move this up here, and I'm gonna see what resistors I have. Probably gonna be using something like 200R maybe. 200, 270, and 470. And I'm gonna see which ones I use here. So 200R, 270, no, and 470. Should have the 470R. Really? So what do I use for the diode here? 470R. Oh, of course. I don't want to match the whole word. So I have 470R there, 470R there. And what about 200R? Mm, 270 then. Got some 270R there. So we can use this resistor, and then just, let's see, and just go over here and connect them like this. So when I set the types of the pins, I do it from the datasheet, and if I cannot see that some pin is specified as open drain, I just set it to output. And when I do that, then the DRC checker will warn me about connecting multiple outputs together, because that can create a short circuit if they're both push-pull. Okay, and I'm just gonna annotate this, and then I'm gonna run the DRC again. No, 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 no. Annotate. And running the DRC again. Let's see what it finds. 27 errors down to 25 errors. Test mode should actually be an input. But what I find very annoying is that I cannot go to the second component here. I can go to J1, but I have to search for U30, pin 41. Like, yeah. U30, pin 31. Yeah, good luck with that. Where's pin 31? Pin 41. Okay. So pin 41, the test mode. I have to check what type of pin is this. Did I make a mistake when I created the component, or is it something else? So where is my data sheet for this chip? Here. Obviously, a bidirectional pin should never be connected directly to ground. This pin must be tied to VSS for proper operation. Buffer type VIS. Yeah, it looks like it's an input, but I want to see what VIS means. Where is buffer type? Let's see, VIS. What does it mean? VIS, voltage Schmidt triggered input. That explains why this connection can be made, but the pin type is wrong here. So this test pin should be an input. And I'm gonna save that, and now I should be able to run this. Let's try to fix some more problems here. So we have pin 5 on U9 and U8. Power output. Since when is this power output? This is supposed to be a power input. Yeah. Great. So, pin connected to some other pins, but no pin to drive it. VDD bias. So the way I solve this kind of problem is just add a power flag there. Because we have the ferrite bead, and the power is getting there, but KiCad cannot know that this is intentional. So therefore it warns about it, but it's no big deal here. And then we have this one. Same here. So let's add a power flag here. Pin connected to some other pins. So VDD33TX. This is probably an output actually, or is it? No, this is not an output. Now so okay, so we have it connected there and we have it connected down there, and this warrants two power flags here. So we got one power flag here, invisible, and then another power flag right here. So conflict between pins. Right, VDD-CR. Let's go back to this datasheet. Pull up, pull down. I'm just gonna check here. So power pins are P, but is there a power output and power input distinction? Let's see. VDD12TX1. Let's find out. This pin is supplied from either internal supply or from device internal regulator. This pin must be tied to the VDD12TX2 pin for proper operation. Transmitter power supply. Okay. And what about VDD-CR then? Bias supply and VDD-CR. Digital core power supply. Supplied by on-chip regulator. Decoupling capacitors in parallel to the ground should be used on pin 6. Okay. So here they're shorted together. And what about the schematic of this evaluation board? Let's see if we can find VDD-CR. Yeah, and here they're shorted together as well. So the question is, what should I define them as? Should I make them power? Should I make them passive maybe? See. This is actually, yeah. Okay. What options do we have? Let's make them unspecified for now. Because I don't really know what to assign to them. They're supposed to be power, they're kind of like power outputs, but they're only power outputs in order to connect bypass capacitors to them. So they are not actually power outputs in a traditional sense. Let's see. Pin connected to some other pins, but no pin to drive it. Pin not connected. Pin 4. Pin 4 not connected. Interesting. Do we have a hidden pin here, which we forgot to connect? Obviously we have, which is not good. Let's do it like that. Or no, wait. Let's see. That is an NC pin, so we can set the type to not connected. Actually, that's better. That would be correct. Okay, I'm gonna run this again. So from 25 errors to 24 errors. That's lots of progress. Hmm. What about VDD 3v3? Did I forget something here? So we have the... Right, I forgot the power flag here. Obviously I need to have a power flag there. From 24 errors down to 21 errors. Okay, GND, problem between pins. Is connected to U30 power output. So power outputs connected together is not really popular with KiCad. Power output. Let's make this passive. Pin connected to some other pins, but no pin to drive it. Yeah, so this power flag is not connected. That's why. Alright, so unspecified was apparently not the correct way to do it. So maybe I should make them passive. I'm gonna see what the internet says about this. Let's see. Okay. Yeah. So the KiCad seems to suggest that you would make only one of them would be power output. Which is kind of that's kind of a hack, yes. But that's something that we'll have to live with for now. 13 errors. Let's see. So here we got a fuse, so we need a power flag as well, because we have a power input. Let's see here. So power flag goes here, and then power flag also goes here. Great. So let's see what else we have here. Right. Okay. Let's make this GPX actually, because they are not supposed to be connected together. So I'm gonna make this GPX. And then I'm gonna go up here and I'm gonna add a few extra labels here. No? Yeah, there we go. So SCK, go here, and this one gets removed, and another resistor gets placed here. And wait a minute. This is weird. So we got two GPIOs, ENC1, ENC2, right? So we got MISO, GPI MISO is actually right. So yes, okay. So now we're gonna fix this because I moved all of the labels. I got these pins messed up, so I have to make sure that everything is connected correctly here. So we got, yeah, and now we're gonna add another one actually. So I'm gonna move this one here. Let's see, and then, come on, yeah, and I'm gonna move this one, and I'm gonna connect this one there, and this one will have another resistor here. And then this one will be GPX, and this one will be also GPX. So GPI and GPX MISO. And then I'm gonna have to add another one, another label here, and another resistor here. So this one will be GPX MOSI. All right, time to annotate and rerun the DRC. So we got 13 errors. Let's see how many errors we get now. From 13 to 10, we got PVDD. PVDD. So PVDD1, is that supposed to be an input? Something tells me it's supposed to be an input, but I have to double check. Should I connect it to any power supply? Of course it should be connected to power supply, like, damn it. Look at this. So we have PVDD1, PVDD2. We're not using PVDD2, but this is the main power supply, so this has to be connected to VMOT. Yeah, this has to be connected to VMOT. This is a major problem. So major that this circuit wouldn't work if I were to leave this as it is right now. So, VMOT. And of course here as well, VMOT. Alright. And then we have the AVDD, but AVDD is actually can be a passive pin, or actually wait. So AVDD is actually a power output, because this is just let's see. This is just a pin that's connected to internal regulator. So this is a power output. And A, G, and D can be a power input. Okay. Seven errors. Right. Do we have a power flag on the VMOT? Does vmod have a power flag? No. So vmod has to have a power flag. Let's place the power flag here. DRC again. Six errors. VCap. VCap should be a passive pin. And it's probably a power input. Yeah. Let's see. Passive. Let's rerun this. Should have 4 errors. Different net assigned to a shared pin in another unit of the same component. Interesting. Different net. Is assigned to a shared pin in another unit of the same component. Wait a minute. Okay, so connected to some other pins, no pin to drive it, which means we need to have a power flag here. No connect symbol found on this pin. Okay, here we're going to put a no connect, and I'm going to put a power flag on, let's see, up here. So this should be a power flag here. Okay, so what does this actually mean? Let's see what this component looks like. Does it have several units? Number of units. That looks very strange. So, oh, wait. This is totally messed up, of course. This is totally messed up. This needs to be fixed. How could I miss something like that? This is a SOT 23.5, meaning that 1, 2, 3 is G and D. Let's see. So 1, 2, and 3 would be the G and D pin, which would be connected to the positive. I think pin number 3, let's see. Pin number 3 is supposed to be connected to the positive lines. Yeah, so this is actually pin number 3, or supposed to be a pin number 3. One, 2, 3, and then 4 is the second or the third input, IO3, and 5 is VCC. Okay. So this is much better. This should fix all of the errors. Alright. So schematic is reviewed. All of the DRC errors are fixed. And time to move on to the layout, I guess.